Okay. Now we're finally at the actual equilibrium part of the solubility chapter. All we've done up till now for the first two periods for you guys, same period here. First two times, all I did was do a little bit of review. Review being how to get molarity, how to do the dilutions. Okay, but now we're going to actually do the equilibrium. It's called KSP. Okay, what is that going to be? Well, we've seen Ks before. We've seen equilibrium problems before. I mean, going back, don't have to copy this, but going back to, we originally saw it, like I said a little while ago, liquid plus energy yields vapor, phase equilibrium. Okay, there were no calculations at all. Then we saw Kc, where we had to do, AA plus BV yields CC plus DD. Now, granted, you didn't write that every time, but it was a chemical reaction, NaO2 plus H2, whatever. It was chemicals that came together, and you figured out the Kc was going to be C raised to the C power, D raised to the D power, over A times B, raised to their powers. Okay, you did all that knowing what we know about kinetics, assuming a one-step mechanism, and all that stuff. All right, so that was Kc. Now, the next chapter, so here, this is Chem 1. This is the first Chem 2 chapter. Now, the next Chem 2 chapter, we figured out Kw and Ka, and specifically Ka and Kb. All right, where we had this equation. We had a specific equation. We had HA, representing some generic acid, plus water, yields hydronium ions plus negative ions, whatever the 8 ions were. And that actually became a little bit easier because we were able to simplify it two ways. One was we no longer had to have all the reactants and products included here. We had the hydronium, we had the negative ion, all right, raised to their coefficients, and we had HA, but we did not have water because water was constant, remember? So it got one guy out of there, and because by definition, unlike Kc's, which could be large or small, by definition that Ka has to be small, we were able to make the problems easier to solve because we didn't have to put x's in there. All those subtracting x's anywhere it showed up, adding or subtracting x's in these problems, we could ignore them. All right. Well, this is going to be even easier. Okay, we are now going to do KSP. That's what it says up there, KSP. All right, KSP isn't even going to have a denominator, as you'll see, all right, when we do this. So each one of these has gotten progressively, since we started Chem 2, has gotten progressively easier. All right, and this one will be the easiest of the bunch. But it's going to involve the same basic concepts of equilibrium. The equilibrium for this guy was a chemical reaction. The equilibrium for this guy was a specific chemical reaction of an acid reacting with water or of a base reacting with water. The equilibrium of this guy is not a chemical reaction. That's the crazy part about this. This guy is going to be the equivalent of this, where salt breaks up into sodium ions and chloride ions. That's the equivalent of what we're doing. Just dissolving salt in water. But it turns out that if you have slightly soluble salts, that is a reversible reaction. All right? All right. Pretty much everyone is going to eventually hit a saturation point. So, but the small KSP ones, the ones that are only slightly soluble, that's what we're going to be solving for the most part. We're going to be solving for KSP, and that's my equilibrium expression. All right, it's going to be for a physical change, not a chemical one. Okay, let's do this. All right, so basically, KSP measures the extent to which a slightly soluble solute dissolves in a solvent. If it's slightly soluble, well, you already know a little bit about what K means. What would you expect the size of K to be, where a lot of it's, not very much of it's actually reacting or dissolving? Going to be very large or very small? It's going to be very small. Yeah, just like when we talked about weak acids. We didn't have to do a Ka for a strong acid. We had to do it for a weak acid. The same thing's true for slightly soluble salts. It's going to have a very small KSP. First one we're going to do is going to be times 10 to the negative, I don't know, 9th or something like that. Very small. All right. So basically, given this equation, this is just an example, given the equation of barium chloride, breaking up into barium and chloride. Notice something here. I already got this question last period. Notice, barium chloride, if we were doing this in Chem 1 for most of the year before we got to the solution stuff, if I told you barium chloride on a test like that, you know what you would have written? Barium plus Cl2. Okay, that's what you would have written. That's a decomposition chemical reaction. That is not what's happening here. This is simply dissolving in water. Okay, he is not breaking up into chlorine gas and barium metal. He's dissolving in water. All right. Now, what would the equilibrium expression look like if this were back in the first time we ever covered Kc? It would look like this. I think you'd all agree. It'd be the products raised to their coefficients over the reactants, correct? Yep. And there it is. Copy that down. And we'll show you how it's going to be a little bit simpler now. Because barium chloride, by definition, is a slightly soluble salt. We know that. We're told that in the problem. Not much of it's going to actually dissolve. It's going to be a very small amount. So once again, I'm going to be able to remove him from the denominator here, right? And bring him over and make a new. We did that before with water. Remember when we did it with water from Kw for Ka? And we made Kw, or we made Ka. Now we're going to make Ksp, okay? Because that barium chloride is not, the one on the left, is not going to change much. It's basically constant. Because so little of it actually dissolves. You don't really need therefore, it's kind of redundant it becomes. But this is what the equation becomes. If I'm not going to include him in the denominator over there, look at how simple the equation becomes. It's just going to be the product. It's not even going to be a denominator. That, like we were happy to see last time to get one of the guys out of the denominator and be able to use a simplifying assumption. Here, I don't even have a denominator, so it's even easier. So each one of these has gotten easier. This is one of the shorter. I think this is the shortest chapter of Chem 2, period. All right. When we're done with this one, we're going to review a little redox and do electrochemistry, which we have not done yet. And then we're going to do a couple of other things. Towards the end of the year, we have a science fair for the middle school. We're going to be preparing that. But basically, this is the shortest chapter you'll see in Chem 2. We could have, technically, if I wanted to, probably could finish it even by the end of the next marking period. But the marking period is over next week, one week from today, and so I don't want to rush it. Plus, I'd have to grade it all, put them all online, and I don't want to do that. And plus, I have lots of grades in this marking period. I'll need more actually in the next one. All right, let's do an example of this. A very simple problem, okay? And it's going to follow the same pattern as what we saw in every equilibrium chapter we've done so far. First, I'm going to show you how to solve for K. Then I'm going to give you K and show you how to solve for X. And in both cases, still, I've got in each class 1 or 2 people in the last test. I'll give you those grades at the end of the period. The last test, at least 1 or 2 people per class has still done it. Solving for KSP, they're solving for X. Given KSP, they're solving for KSP. I mean, they're doing the opposite of what you're being asked to do. So, I mean, I don't know how much more I could, do of these, but it's showing up again. Here's your first example. And it shows you, when I see things like that, it's hard to give any partial credit because it's fundamentally misunderstanding the question and what it's asking you for. Okay? It's one thing to make an algebra mistake, a math mistake, forgetting the multiplier, square a number, You know, that can be done. I don't. And it's 1 point off, 2 points off, whatever. But when you're solving for something it already gave you, you know, that is hard to overlook. It's hard to give you partial credit. All right, notice already off the top of, you know, what you have to do. I'm given grams and I'm given liters, and this is going to be the case in almost every problem you have. Guess what I have to do first before I even begin the problem? I have to do a molarity, right? I have to do a molarity. So let's do that first. Here in class I had to start the equation and then do the molarity. I think I'll do the molarity first here and then do the equation so we don't have to worry about leaving space. So molarity, molarity, just like we learned how to do last couple of days, last couple of periods. Molarity equals moles of solute over liters of solution. I know I have 0.0435 grams of solute. I'm going to convert that from grams to moles. 1 mole contains, add them up. What do I have to add up? 2 Ks, 4 Os, 1 S. What do I get? 174.25 grams. That's my numerator. Do the math for that part. And what am I dividing by? 2.0 liters of solution. Give me my molarity. It's going to be a very small number, probably times 10 to the negative something, fourth, I think it was.
1.25.
All right, there's only 2 significant figures, so 0.0002, 125, 12. Is that right? 0.00013 then? Is it point? Is that right?
125. Well, round 5 got rounded, so it's 1.
So it's 12. That's right. If it were, for example, 0.0001249, that's still 0.00012.
Mine just gives me 1, 2.
Whatever. You probably have it. I don't know. Maybe the decimal is like rounding to a specific part. I don't know. Either way. All right. So it is 12 then, not 13. Let me erase that. Just make sure. Wait, 0.00012. Molar. All right, now that's the molarity. Now it's time to do the KSP problem. So I write the equation like I always write. If it was HA plus water is hydronium to hydroxide, you know, AA to the BB, all that stuff. This one's going to be what? What's my equation going to look like? Well, it's just K2SO4 solid breaking up into what? K plus SO4. You do have to, and by the way, I'm going to pass these out. Somebody asked for these last period. I thought you guys already had them, but I guess you don't. Common ion sheets, I gave them to you last year. We haven't really used them a whole lot this year. You're going to need them not only for this chapter, but for the next one. All right, that's not enough. I got to write that correctly. K has a +1, SO4 is a -2, and if you don't know the charge, if you don't know the common ions, they're on the sheet. All right, you should know a lot of these: sulfate, chlorate, nitrate. You should. 2 goes in front of here, and a little AQ next to him. And a little AQ next to him. Okay? All right. Now, this is weird. I know, and I actually looked it up today because I wasn't sure about this. It's kind of strange. Your concentration, this is telling you this is the amount that actually dissolved in solution. And you put that over here, and it kind of is weird because in reality, that's not normal. Normally, if we're doing an equilibrium problem, we would have the total amount here, and then this would be 0, 0, minus x, you know, that's what we would have. But in this case, I don't really have to do that. It's telling me that's how much of, I mean, by the way, to make this solution, I'm going to use this solution for a demo probably tomorrow or the next day. This is a saturated potassium sulfate solution, the same problem I'm doing right here. To make a saturated solution, I actually throw in to, like, in this case, about 500 milliliters of water. I throw in way more potassium sulfate than could possibly dissolve. All right, I just, you know, maybe 15, 20 grams. And then I let it stir up for like 15 minutes. Then I pour off, at the bottom will be a layer of potassium sulfate. I just pour off the stuff at the top. That's saturated. All right, the amount that actually dissolved is that much. All right, so basically it's saying that's the numbers that are over here. 2, in this case, 2 times that, because 0.00012 molar and 0.00012 molar. That's the actual concentrations that dissolved not the amount that I added to the beaker. In the case of Ka and all the other Ks we've calculated, it was we were kind of, remember, this guy's kind of being ignored. The amount I put in is pretty much getting ignored because it changed by so little. And you can see how little it changed. It changed very little. It only lost that much of whatever I added in. All right, so now I've got, so basically this is, if you look at your notes, or your book I should say, which I know you don't read a whole lot, it'll even write here, dissolved. All right, that's the amount that actually dissolved, instead of just assuming that's the initial. So that's why there's not ICE, okay? Now, lastly, we got to plug it into the KSP. KSP is going to equal products raised to their coefficients, which would be K squared times SO4 to the first power. So that's easy enough. What's my K concentration going to be? 2 times 0.0012 or 0.00024, right, molar, squared times 0.00012 molar gives me what? Very small number. What is it going to be? It's going to have to be times 10 to the negative what?
6.9 times 10 to the negative.
Wait, I don't think that's the same number I got last period. What was it?
That's what I got.
6.9 times 10 to the negative
12.
12? Oh, I thought there was a negative 9, but I guess I could be wrong. I just thought I remembered it different. Okay.
Why'd you square the?
Why do I square that guy?
Yeah.
K squared. Remember, that's the expression, the KSP expression. Look at it. Yeah. BA, CL raised to the second power. Basically, it's the same as the other one. It just doesn't have a denominator.
Okay.
All right. All right. So, whoops. Now, what does that tell you? Well, it tells you the size of KSP tells you very little of this stuff actually dissolved. All right. In a 2-liter solution, 2 liters, you only got 0.0435 grams dissolved. Okay, that's not a whole heck of a lot. Okay, and that makes this the KSP. By the way, I wonder if I actually looked that one up. If that actually is the KSP of potassium sulfate. The important part is potassium sulfate. We're going to use this in a demo coming up pretty soon. Probably not tomorrow, but maybe the next day. All right, your homework is, I don't know if I put it on here or not. I don't think I did. Homework is page 843, numbers 8 and 9. And I will call you up and give you your test grades